Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Harith Azra bin Zaili, and our group will discuss about the article which is the application of ceramic based on concrete waste by spark plasma sintering. For the introduction, as mentioned in the title, this experiment is done in order to create a ceramic based on concrete waste, which is from recycled aggregate powder RAP that consists of calcite and quartz. However, we know that this recycled concrete produce a low quality concrete due to residual waste cement. So, in order to develop a ceramic compact with high mechanical properties, this experiment is using the spark plasma sintering (SPS) method. This SPS method, which sinters raw material powder within a graphite mold under compression pressure, lowers the sintering temperature and produces material with superior mechanical properties. The benefit of SPS process include low processing time, high density, high purity, and improved mechanical properties. For the objective, the experiment, the article is to fabricate a ceramic using RAP by applying the SPS method. Next is to observe the relationship between relative density, mechanical properties which is flexural strength and modulus, and surface structure at different sintering temperature.
Next, we move to procedure to create the ceramic based on concrete waste. There are few main steps in this procedure. First is material preparations. Next is spark plasma sintering (SPS), and last material characterizations. Next, the first main step, material preparations. For material preparation, the recycled aggregate powder RAP was prepared by crushing, sieving, and pot milling of concrete waste. This concrete waste with a fine aggregate composition consists of sea sand, limestone, and the shell of sea creatures. Thus, the composition of the use of concrete waste is expected to be calcium rich as compared to that typical concrete waste. The concrete waste was crushed into 10 mm length cubes using a jaw crusher. Then the crushed concrete waste was sieving using an open sieve of mesh size 425 micrometer, and then milled using a pot milling apparatus. After the pot milling, the RAP slurry was dry for 2 hours at 393 Kelvin. Then we measure the particle size distribution of RAP using a particle size analyzer, and the average size that we get was 9.4 micrometer. Next, spark plasma sintering (SPS). The raw material that we get from material preparation was poured into a graphite mold capped by pairing two punches of 50 mm and a die with inner 50 mm and outer 90 mm. The graphite mold was covered with a carbon felt to prevent heat from radiating out during the sintering process. For the SPS sintering condition is 24 megapascal pressure, 20 minutes sintering time, and 1123 to 1273 Kelvin sintering temperature was set, and the heating rates were 42.5 to 50 K Kelvin per minute. The holding time for each sintering temperature was 5 minutes. Then the current was turned off as the holding time elapsed, and the cooling rate was furnace cooling. Subsequently, the sample were removed from the graphite mold. The SPS sinter compact was 5 mm thick with a diameter of 50 mm. Next is material characterization to analyze the material properties of the material produced. We are using 4 tests. is three bending point, weakest harness, SEM, TGA, DTA. And first, we do a 3-point bending test was performed on specimen obtained by cutting the sinter compact into bars. This bar was 7 millimeter in width, 40 millimeter length, and 3 millimeter in height. We attach the string gauge at the bottom of the center of the specimen. The specimen were used for each SPS condition. There are three conditions based on the centering temperature. The three bending test was performed with a 0.5 millimeter per minute crosshead speed at a 40 millimeter support span. In condition, the stress strain curve was recorded using a digital oscilloscope, and the flexural strength was calculated using typical formula. Furthermore, the flexural modulus, which is the slope of the strain curve is in the elastic region, was calculated using the least square method. Next, the weakest hardness test was performed on the specimen surface after the 3-point bending test with a load and a loading time of 500 gram and 50 seconds respectively. The specimen was divided into 5 parts from the specimen center. The measurement was conducted at time point for each division point. To avoid indentation, load influence of flexural strength and modulus, we use the HV specimen after the 3-point bending test. However, work hardening did not occur in the HV specimen due to the sintered compact being ceramic. Thus, the HV values are not affected by 3-point bending test. Next, the surface structure of elemental composition of the sintered compact were observed and analyzed using SEM EDS. RFP thermal analysis was performed using TGA DTA apparatus up to 1623 Kelvin temperature and 20 Kelvin per minute heating rate under air and nitrogen gas environments. X-ray fluorescence analysis was performed on EDS 8000.
For the result and discussion, this first figure is obtained in order to investigate the fundamental characteristic of RFP, which is by conducting the SRD method. As we can see in this slide, the first figure shows the result of SRD pattern of RFP, which is the RFP chemical component constitute mainly a calcium oxide and silicon oxide with a small amount of aluminum oxide and ferrous oxide. From the result obtained, the peak show the presence of calcite and quartz. So, the chemical composition of calcium oxide is categorized mainly as calcite, which is derived from whisk, cement, and fine aggregate. Next, the figure 2 shows the result of the relationship between relative density and sintering temperature. As we can see from this graph, the relative density linearly increased to almost 1 as the temperature reached at 1223 Kelvin. And when the sintering temperature increased from 1223 to 1273 Kelvin, it results in a decrease in relative density. This decrease occurs because of the melted RFP that is observed around the graphite punch after raising the temperature to 1273. And this indicates that the melting occurs during sintering at over 1223 Kelvin due to the generation of micro inner pores at temperature close to 1273 Kelvin.
Next, we move to the figure 3, which is relationship between the HV, weaker harness, and the distance from specimen of 3-point bending test specimen. In this test, the distance was measured using the average line at 2, 6, 10, 14, and 18 mm. The weaker harness distribution within the SPS sintered sample almost uniform for each sintering temperature. As we can see in the graph, At the lower temperature, which at 1123 Kelvin, the Vickers hardness almost uniform for each distance, and at the higher temperature also the same. The Vickers hardness also show the uniform graph, uniform pattern, and the average HV of the 5 points increase with increasing sintering temperature. Okay, we can see here at lower temperature, the value of Vickers hardness is lower than the higher sintering temperature. When we compare here at 1123 Kelvin, the value of the Vickers hardness is below, slightly below than 150 HV, and for the higher temperature of sintering, we can see here the Vickers hardness value is um, between 350 and 400 HV. So maximum value obtained was 393 Kelvin at 1273 Kelvin, which is the higher sintering temperature for this test. When we compare to the concrete HV, the concrete HV only obtained 100 HV only. We can conclude that using the SPS method, we can achieve the higher Vickers hardness value compared to the normal one, concrete. This is because different curing process between the concrete and the SPS method. For the figure 4, the relationship between the mechanical properties and sintering temperature. As we can see here, the flexural strength increased linearly from 30.4 megapascal to 74.2 megapascal as sintering temperature increased from 1123 Kelvin to 1223 Kelvin. For the flexural strength, it is represented by the circle ones, and the flexural modulus represented by the triangle ones. And for the flexural modulus, we can obtain the maximum flexural strength at 78.9 megapascal and 91.4 gigapascal of maximum flexural modulus were achieved at 1273 Kelvin. When we compare to the flexural strength of concrete, which at only 16.9 megapascal. So again, we can conclude that SPS method is better than the normal concrete method because we can achieve the higher flexural strength using the SPS method. Thus, SPS sinter compact exhibit satisfactory mechanical strength for use as construction material. To investigate the microstructure of the SPS, we are using SEM, scanning electron microscopy, and the result shows in this figure. For the figure 6b, which is at the top of the graph, top left, they show the two types of particle we recognize, such as dark gray particle and gray particle. The 6b, the top one is at temperature 100 and 1123 Kelvin, and the for figure C, which is at the top right, as sintering temperature increased to the 1173 Kelvin, the surface flattened and contained dark gray and gray particle. And the for figure 6D, which is at the bottom left, the flat surface and some pores were visible. The dark gray particle remained on surface and gray particle disappeared. This is at temperature 100 to 1223 Kelvin. When we compare between C and D, the gray particle is disappeared. Okay. For the figure 6E, the micropore uniformly distributed on the surface containing dark gray particles with few pores. The micropores generated by the inner gas as it resulting from melted gray matrix due to the increasing of temperature. In this graph, in this micrograph, we can see here the compositions of the elements consist in our specimen. So, to obtain the compositions of the elements, we are using EDX, SAM EDX. Uh, for the lower temperature 1123 Kelvin, the is contain dark gray particle and asperity surface. When we increase their temperature, it consists of dark gray particle remain as before, gray particle also remain as before, and flat surface, which is the asperity surface is disappear. Not disappear. The asperity surface are transformed to the flat surface. And when we increase its temperature, the small asperity 2 are and small asperity 1 are formed in our sample, which is the gray particle is disappeared. And at the higher temperature, which is at 1273 Kelvin, the dark gray particle only the dark gray particle and micropore exist. So as we can see of at the composition of oxygen, silicon, calcium, and carbon for each temperature is different. Some of the composition are reduced, and some of the composition are increased. So the last discussion is figure 7, which is to analyze the liquid phase centering phenomena of the SPS process using RAP. We conducted TG-DTA curve. So for the figure A, the TG-DTA curve test in air, and for the figure B, it tests in the nitrogen. Uh, as we obtain the result, the the result is similar to the previous studies, which is the characteristic of the RAP from the previous study and our sample is almost similar. So this is just another test to compare our specimen, our sample, and the previous sample. And it looks like similar from the previous sample. And the endothermic peak around the endothermic peak around 1000 to 1023 Kelvin, and it slightly decreased TG show the RAP melting phenomenon.
In conclusion, this project is to develop a novel method for recycling concrete waste. This study fabricated ceramic using recycled aggregate powder (RAP) while applying the SPS method. In particular, the effect of sintering temperature on the mechanical properties of the RAP compact was investigated, and the results are summarized as follows. First, the maximum reactive density was 1.0 at a sintering temperature of 1223 Kelvin, but it decreased at 1273 Kelvin. Next, the density gradient was not recognized in the proposed sintered compact because the HV was almost uniformly distributed. This maximum HB was 393 at a sintering temperature of 1273 Kelvin. Next, for the pressure strength and modulus of the proposed sintered compact is increased with sintering temperature. The maximum pressure strength and modulus were 78.9 megapascal and 81.4 gigapascal respectively at sintering temperature of 1273 Kelvin. For the TGA result, the TGA DTA curve of RAP and displacement of SPS processing show that the RFP melting phenomenon over 1223 Kelvin. Therefore, the mechanical properties at certain temperature of 1273 Kelvin were improved due to the enhanced wettability between the sand particle and the grey matrix by the progression of the liquid phase sintering phenomenon. Last, the sinter compact beyond a sintering temperature of 1223 Kelvin was composed as a dark grey inclusion and a grey matrix-like composite material. SAM EDX element analysis results show that the dark grey inclusion was silica rich and sand particle in the waste mortar. The grey matrix was generated by melting the waste cement and fine limestone aggregate. That's all from us. Thank you.